Hello, welcome again to our physics online class. Today we are going to discuss on the topic of electromagnetism, and we are going to discuss on the subtopic of magnetic field. We are going to cover different parts of magnetic field. Now let us start our discussion by defining what is magnetic field. We define magnetic field as a region where a moving charge or a current carrying conductor experiences magnetic force. It is a region where if a moving charge or a conductor is present there, is going to experience magnetic field. Now, when we are speaking on a magnetic field on a current carrying conductor, we need to consider an experiment which was done by a scientist called Oersted. Mr. Oersted did an experiment with this arrangement. We can see the circuits here. This is the normal arrangement of the circuit. He allowed the current to flow through the conductor. This is the wire. Now, when the current was flowing through the conductor, the compass needle deflected in one direction. And when he reversed the current to the other direction, also the compass needle changed the direction of deflection. We summarize by saying that he observed that magnetic compass needle was deflected when placed near a current carrying wire. And he concluded that a current carrying conductor is always accompanied by magnetic field. So we may say that wherever a current is flowing through the conductor, magnetic field is generated. And if you reverse the direction of the current, also the direction of the magnetic field will be reversed. Now, magnetic field are represented by lines of force. Therefore, when you want to indicate that this area or this conductor is having magnetic field, we are going to draw the magnetic lines of force. These are imaginary lines drawn to represent the presence of field. And the shape or the structure of the lines can be traced by using a protein compass or iron fillings. Now, the direction of the magnetic field is given by the right-hand grip rule, or sometimes we use a screw rule. But in this session, we are going to discuss right-hand screw rule alone. The right-hand screw rule states that when a wire is handled or clipped using a right hand with the thumb pointing in the direction of the current flow. Then fingers curve indicate the direction of the magnetic field. The meaning of this rule is that we have indicated in this diagram. Assume you hold a wire or a conductor by using your right hand as indicated here, and your thumb is pointing on the direction where the current is going. Here the current is going upward. Then your curling finger will show the direction of the magnetic field. Now, if it is a straight conductor like this one, therefore, magnetic field will move on the direction indicated in this diagram. We need to note that when the current is moving in a curved path, when a current is moving in the curved path, then the thumb will represent the direction of the magnetic field. Therefore, the thumb sometimes represents current and sometimes represent magnetic field. It depends on how the current is flowing in that circuit or conductor. Now we have a way of indicating the direction of magnetic field or current on the conductor. The first way, we use a dot. When you see a dot in the diagram or in any structure of magnetic field, that dot indicates the field lines or current is flowing out of the paper, or is pointing out of the paper, or is pointing upward. Now, in order to understand this concept, imagine where you are sitting, and then you have a paper on the table, and then you are looking that paper on the table from the top. Now, when you see a dot, means the field or current is coming upward, or is coming out of that paper which you are looking. Therefore, the current is flowing towards you. And the second way, we use a cross. We use a cross. When you see a cross, indicates the field lines or the current is going into the paper or downward. We use the same concept as before. Imagine you place a paper on your table, and then you are looking that paper from the top. When you see a cross, means you see a tail of an arrow, and that shows the field or the current is going downward or into the paper. That is why you see a cross which represent a tail of an arrow. We are going to check on the structure of the field lines for different shapes, for some of the shapes. The first, we are going to check on the field lines due to straight wire carrying current. We are going to check on two cases: when the current is upward or out, and when the current is downward or into the paper. On the first case, when the current is upward or outward, we said we use the dot to indicate that thing. Therefore, here we have a dot at the center of this circle. Now, this dot indicates that the current is going out of the paper or upward. Therefore, if we imagine you are looking at a paper on your table, and then you want to indicate that the current is going outward or upward, I'm going to point the thumb upward. I'm going to point the thumb upward. Or I'm going to point the thumb out from my screen of a phone or a laptop. Now you will find that the fingers will curve toward the direction of this arrow indicated here. Therefore, the direction of the fingers will be representing magnetic field. The second case, in this figure, we say the current is moving downward or into. You will see here a cross. You will see a cross. Now, a cross, as we said, is representing current is moving into the paper or downward. Now, if I want to show that the current is moving into the paper, I'm going to point a thumb, which now will show the direction of the current, downward or into the paper. Or I'm going to point the thumb towards a screen of my phone or my laptop. You will find that the fingers will curve towards the direction indicated by these arrows here. The second case, we want to check the field due to a circular coil. How are we indicating the field due to circular coil? Now, if we consider the field due to circular coil, this is our circular coil here, this bolded line. Now we will find that the current will be flowing on the circular coil in the curved path. We said before that when the current is flowing in the curved path, then the thumb will indicate the direction of the magnetic field. Now here, what you are going to do here, you put your fingers to be in the curved path in the direction of the current in the circular coil. And then you put your thumb straight. You will find that the thumb will point towards this direction, which is the direction of the magnetic field on this circular coil. And the last for today, we are going to check on the magnetic field due to a solenoid. Also, when you are considering a solenoid, the current is flowing in the curved path. The current is flowing in the curved path. Therefore, you are going to put your fingers in the curved path toward the direction of the current. Then you are going to put your thumb in the straight line. Therefore, the direction where the thumb will be pointing will be the direction of the magnetic field. Therefore, these are called field lines. These are called field lines, are representing the magnetic field, availability of the magnetic field on the conductor. And their direction is determined by the right-hand grip rule, as we have indicated. Now, let us check on the property of the magnetic field lines. Property of magnetic field lines. The first property, we say magnetic field lines never intercept. We mean they will never cross each other. The second property, we say the tangent to a line of force at any point gives the direction of the magnetic field at that point. A tangent drawn to a line of force at any point will indicate the direction of the magnetic field at that point. The third property, we say the magnitude of the flux density is directly proportional to the field lines per unit area. Therefore, if we have many magnetic field lines at a given area, that shows that the flux density or magnetic field intensity is larger. The greater the number of field lines, the higher the magnetic field at that point. And the fourth property, we say the parallel lines always will imply a uniform magnetic field. Parallel lines always will imply uniform magnetic field. Now, let me demonstrate or elaborate this property by drawing what we mean. For example, if you are having these field lines, in this shape, assume these are the field lines, which indicating the variability of magnetic field. Now, this is the correct way of drawing, but we cannot draw the field lines to cross each other. We cannot draw this way. You draw field lines crossing each other. This is not a correct way of drawing. That is the first property. The second property, we say the tangent at any point on the line of force. Assume we have a curved line of force like this one. This is the curved line of force, means that the magnetic field are flowing in the curved path. Now, when you draw a tangent at any point on that line of force, we say this tangent which is drawn will indicate the direction of magnetic field at that given point. Will indicate the direction of the magnetic field at that given point. For example, if it's point P, like that. And the third property, we said the magnitude of the flux density is proportional to the field lines per unit area. Now, assume you have these field lines drawn in that way, drawn in this way, drawn in that way, drawn in that way. Now we have these field lines. We have these field lines as indicated here in this diagram. We have these field lines as indicated here in this diagram. Now, if you have an area like this one, this is an area we are going to refer. Now here, the number of field lines here is different from when you consider the same area with the same dimension at this area. Therefore, here we say we are having large magnetic field or magnetic flux. And here we say we are having a smaller amount of magnetic flux because the number of lines at this given area is smaller. And the other property we say when you draw straight lines, like this, the straight lines will always indicate uniform magnetic field. And the curved lines like this one will indicate non-uniform magnetic field. These are the property. These are the property of magnetic field lines, which we have discussed in this part. Let us now discuss how we can obtain magnitude of magnetic field for different conductors. We have two laws which are used to determine the magnitude of the field lines for a given conductor. The first law is called Biot and Savart law, and the second is called Ampere's law. These are the laws which are used to determine the magnitude of the field lines for a given conductor. The direction of the field lines will be determined by the right-hand clip rule, as we have discussed. Now, the statement of the Biot and Savart law is indicated here. we say Biot and Savart law state that the magnitude of the magnetic field B is proportional to the current I, the length dl of an element, the sine of an angle theta, and it is inversely proportional to the square of the distance from the small element dl to the point where you are determining the magnetic field. Mathematically, the law is written as indicated here. B is indicating magnitude of the magnetic field. Delta B here represents a small change or a small amount of magnetic field for a small length, which is used to calculate the total magnetic field. Therefore, the magnetic field at that small length is proportional to the current, a small length, dl, sine of theta, which is the angle between the small length and the direction or the line which is combining the small length and the point where you are finding the magnetic field. And R is inverse proportional to R square, which is the distance between the small lengths considered or conductor considered to the point where you are determining the magnetic field. Now, when you remove this constant of proportional sign, we introduce a constant of proportional K. And that constant of proportional is equal to the value as indicated here, mu naught over 4 pi. Therefore, when we take off the proportional sign there, we introduce here mu naught over 4 pi. This gives us a mathematical equation of Biot and Savart law. Now, mu naught is the constant of proportional, is called permeability of free space. Permeability of free space or vacuum. And its value is 4 pi times 10 raised to -7 Henry per meter, or Weber per ampere per meter. These are the units used to indicate the value of the permeability of free space. We are going to see them later. How are they obtained? And when we have just a symbol mu without this note here, that is called permeability of media. Permeability of media. And when we have a symbol mu r, mu with a subscript here of r, that shows relative permeability. Now let me explain the relation between permeability of free space and the relative permeability. They are related. When you are given the relative permeability, you can use it to find the permeability of the media. Now, we say relative permeability is equal to permeability of media over permeability of free space. This implies that the permeability of media will be equal to relative permeability we multiply by permeability of free space. Now, if we are given a media other than air, media other than air, we can write the Biot-Savart law as delta B is equal to mu I delta L sine of theta, we divide by 4 pi R square. And if we are given relative permeability, we may write that equation as delta B is equal to mu R, you multiply by mu naught, you multiply by current, then you multiply by delta L, multiply by sine of theta, and then you divide by 4 pi R square. Therefore, it depends on what you are being given. You may use mu naught alone, you may use mu, or you may use mu R times mu naught to indicate the media on which the conductor is pressed. We have two special cases of Biot-Savart law. The first case, we say when the angle theta is 0, means magnetic field lines are parallel to the axis of the current carrying element. Therefore, if we check the sign of 0 in the Biot-Savart law, will be equal to 0. That concludes that magnetic field will be equal to 0. Therefore, when the magnetic field lines are parallel to the axis of the current carrying conductor, magnetic field is equal to 0. The second case, when the angle is 90, sine of 90 is 1. Therefore, magnetic field will be maximum. Magnetic fields are maximum when the plane passing through the element are perpendicular to the axis of the current carrying conductor. Thank you for watching. In the next video, we are going to discuss on the application of Biot-Savart law in determining the magnetic field of different shapes. Means you are going to use Biot-Savart law to derive the expression of magnetic field for different conductors. Don't forget to subscribe to our channel so that you can continue to receive study material at a right time.